Okay, let's continue with the next video. So the theta here actually is the theta is the degree of this in here, this angle here. So degree of the angle, this one is positive. If it goes downhill, the theta is negative. So positive for uphill, negative for downhill. Okay, and then next we predict the friction. Again, this friction we use Reynolds number, but remember we have a density N, a Vm, we have already got D, and viscosity N. Remember density N, rho N is equal to rho gas 1 minus, is it no slip, 1 minus lambda L, rho liquid multiplied by lambda L, and viscosity of no slip, again viscosity of fluid multiplied by lambda L plus viscosity of gas multiplied by 1 minus lambda L. So if I'm not mistaken, I've already write it down here. See here. Okay. So that's the density and viscosity. We have this number, and then we have epsilon over D. Remember that this one is dimensionless, this one dimensionless. So it's to be feet per feet. It's not feet. It's not inch per feet. It's not feet per inch, or not feet per inch. So remember, I don't want to have the same mistake. Okay. So remember this one. You have to be able to calculate this one easily. Okay, and then we have a friction N, still friction N. So it's no slip already, because this one no slip. So it's a friction of no slip. So we have to modify it again with the constant, correct it to become a slip. So first using the Y, and then using the S. The first Y is lambda L divided by HL over with the degree square. This HL, remember, this HL is the last HL. So whatever is the last HL, use this one. It's not there everything around here. Okay, this HL. A lot of mistake. You just pick any HL. So this HL. Why should we do this L? Because we already done everything here to get the corrected HL. So use the corrected HL. Okay. So this SL square, lambda L divided by HL square. Okay. And then we have a S, this expression, ln of this Y, and then the whole thing. But there is a note in here. If Y equal to 1, so S becomes 0. If Y between 1 and 1.2, so the expression of S is this equation here. Okay. So what is S? S is actually epsilon of S equal to F divided by Fn. So if you have an F, you just use Fn multiplied by epsilon to the power of S. Okay, epsilon of S. So epsilon of S multiplied by Fn, no slip friction, is the friction itself. So this is the expression. Okay, so this one is this A over S. Okay, and then finally we end up with having the last one. So slip, density slip equals this whole expansion, because slip, so you have an HL minus 1 HL for density of gas, and density of liquid, HL liquid. And then we use to calculate the PDL here. It's already been this friction is already have a what you call it degree on it, is corrected everything. And remember that we don't have acceleration. And for the first term, friction rho n Vm square divided by 2 dgc. So use this one, rho n, no slip density. This one is slip density, it's different, okay? In the same equation you have different density. This is a no slip density, okay? And this one is slip density. And this expression is the way they Bex and Brill derive it. So you have no choice but to use this one. And this one is more logical because rho s is the one that you see in the pipe, because no slip actually is the one that you don't see in the pipe. So this one is the actual one. This one is that's the way they do it. That's it for Bex and Brill. So for the data preparation, remember that in the bottom I already give it to you here. So do everything here, and then we will have a homework for this one. So this homework we'll do next week, the 13th, I'm not mistaken, or 14 probably. Okay, March, May 14, if I'm not mistaken. Yeah, May 14. So this homework to May 14, day 3. So hopefully you will able to do that. Okay. This is the example of how you do it. So I will give you much better than this one if so I will not give you a different number. For example, you have a key O and key gas. This is the standard condition from the after separator, and you have all of the what you call it parameters here. So usually I use correlation for these numbers here, not correlation. And then first we have to change the key O to become condition in the reservoir and in the tubing. So multiply by BO, and then we rearrange everything, become this expression. And then we calculate BG, BJ, BG, and then we calculate QG with the expression, and etc. We continue with the lambda L, and we calculate the density each of one. So and then we calculate NFL, and then we end up with having, okay, we have a transition flow actually after we see this condition. After we see this condition, we have transition flow. First what you do is to see that, oh okay, I have to calculate the transition in what is 98, okay, 98 segregated. So this one is you calculated segregated, because transition you have to calculate twice, segregated, and using the parameter of segregated A, B, C, E, F, G, H, and using parameter of what you call it intermittent. Okay, so this is segregated, this is intermittent. So calculate both of them, so you end up with each of them has the same HL. Okay, and then you recombine everything, become an HL. Okay, so this one combine everything A, and then using this equation to become this number, and continue with the density, no slip density and no slip viscosity. So you end up with having Reynolds number, and then you have the friction. The friction is 0.627, and okay, and no slip. Oh, I'm sorry, the friction is 0.02133. So remember, the friction usually is 0.0 something. If you find that 0.6 point something, it's not right. So make sure that you understand this one. So it's around 0.0 something. It's impossible more than 1. So if you have 1 point something, it's possible. Or it's too small, 0.0001 is too small. So around this number, remember that. And then we calculate y. Y, we have an s, and then we have an f corrected from this one to become this one. Then we calculate the s, we have the number, and then plug in the s and y, so we've got the number. So that's basically what we do, and this is the way we do it, and then we find the flow pattern. So please do this homework. I will give this one to you again also. Okay.